Easy. Okay. Yeah, I mean, did anyone really want to take the quiz Monday, or should we skip it? You do have a test Wednesday, like a week from today. Skip. Getting like, okay, little feedback, skip. Skip. Yeah, let's just skip it because we could probably use the class time. Sometimes people want to skip and then other people want to take it for a grade boost and then they end up wishing that they hadn't. Not this particular quiz, but that seems to happen at the end of the semester where people are like, yeah, let's do this to boost points. And then it ends up like backfiring. Okay. So the homework went okay. It took me forever to get your homework up the other day. You probably didn't notice because you were probably watching the video or doing something else. But they cut off my MATLAB access, and I don't even know what happened. Like I could get in, but I couldn't get into our class. It was very bizarre. So I had to sit there and like chat with this person for like 45 minutes while he tried to fix my account so I could put your homework up. It was very strange. Apparently my access had expired, but I don't know. Very weird. All right. We are going to talk about hyperbolas. In 7.2. Hyperbolas. All right, so a hyperbola is another conic section that we will discuss. You'll find that there are a lot of similarities here between the types of equations that you're going to look at for hyperbolas and ellipses and circles. They're all pretty similar, but they have major differences that will cause their shape to be different. Let's see. There we go. Okay. So this is what the graph of a hyperbola looks like. You're going to see that it almost kind of looks like two parabolas. We're going to talk about parabolas next time, and you might be wondering, didn't we already talk about parabolas? We talked about parabolas as far as they were graphs to quadratic functions. In 7.3, we're going to talk about parabolas such that they can be oriented horizontally. So we will get to that. But today, hyperbolas. So these kind of look like two parabolas that open in opposite directions. Now, you might have them open out to the sides, or you might have them open up or down. So a hyperbola is a set of points in a plane, the difference of whose distances from two fixed points called foci is constant. So you've got this distance from the foci that's going to be constant throughout as you work your way through the curve. The line through the foci intersects the hyperbola at 2 points called the vertices. So the line that goes through the foci is this transverse axis that joins your vertices together. So now, depending on the way that hold on, let me see if I can fix this. Depending on the way that your hyperbola is oriented, your transverse axis can either be vertical or horizontal. So your transverse axis contains the vertex points. And remember the vertex, similar to how you saw vertices for an ellipse, same type of idea for hyperbola. And it's kind of confusing the way this is labeled if your copy didn't come out too bright. The vertex is really like you've got these little pieces that are pointing to these points. So the vertices lie on the actual hyperbola, and you're going to have two of them, and they just kind of control these, if you want to think about them as being midpoints here. And then you've got this transverse axis that runs through the vertices, and the foci will lie along that transverse axis. If you want to think about the transverse axis being kind of similar to the major axis for ellipses. The midpoint of the transverse axis is the center of the hyperbola. And just like with ellipses, we're going to talk first about the center being at the origin, and then we're going to move that center to somewhere else on the coordinate grid and talk about just kind of how that changes the properties of your hyperbola. So that's sort of a little bit of the vocabulary that you're going to be seeing throughout. So it's really important that we understand the transverse axis. Make sure we understand that that transverse axis contains the vertices and contains the foci. Now, you can see the difference here between the graphs. When you have a horizontal transverse axis, so not necessarily one that's sitting on the x-axis, that's just because in this case we have a center at the origin. But when you have a horizontal transverse axis, you're going to see your hyperbola opening horizontally. So they're going to be opening left and right. Sometimes students get these mixed up. But if you have a horizontal transverse axis, that means you're opening to the sides. If you have a vertical transverse axis, you're going to be opening up and down. And I think that's a little bit more of an intuitive thought to have. If it's a vertical transverse axis, then you're opening up and down vertically. So these are all the things that we need to consider here. Also, you're going to notice a big difference here are the way that the equations are written. For ellipses, we had a plus sign. For hyperbola, we have a minus sign in between these two terms. Another thing was that for ellipses, we usually listed them as x squared over a squared plus y squared over b squared equals 1, or x squared over b squared plus y squared over a squared equals 1. We usually just listed the x term first, and we just picked a to be the value that was the largest denominator. That's not the case here. With hyperbola, you're going to have a term that's positive and a term that's negative. So the negative term is going to be the one that follows the minus sign. The positive term is going to contain a in the denominator. Remember that value for a is going to lead you to your vertices, same way it does for ellipses. So notice that when you have a horizontal transverse axis, you've got vertices sitting along that horizontal axis, and a is in the denominator for x. You're going to see something similar, opposite case, whenever you have a vertical transverse axis. In this case, the y term is going to be listed first because it's the positive term. And then a squared will be in the denominator. So in this case, a is always going to go with your first term's denominator. So you're not going to just say, okay, this number is bigger, so I'm going to choose that to be a. You don't do that for hyperbola. For ellipses, it is always the case that a is greater than b. For hyperbola, that is not the case. Sometimes you're going to have a value of a that's less than a value of b. Sometimes you're going to have a value of a that's greater than the value of b. Doesn't matter. The only thing you need to know for hyperbola as far as choosing a is that a squared is always going to be in the denominator of that first term, or the positive term. So that's the big difference there. The vertices are a units from the center, the foci are c units from the center. So that does not change. And for both equations, this is different. For ellipses, we had c squared equals a squared minus b squared. For hyperbola, we have c squared is a squared plus b squared. And that's another place where you can think about these as being opposite. So if you're thinking about ellipses having equations that include plus signs, well, the foci equations will include minus signs. Whereas for hyperbola, their equations will contain minus signs, but the foci equation will contain a plus sign. And these are all just things too that, I mean, you're going to have your notes, so you can go through and highlight. In a normal semester, when I have students in a classroom, I would have you make a note card, and I would say, okay, you can bring your note card to your exam, and it would have all the pertinent information on it. So this would be the type of stuff that you would put on a note card. So if you feel like, gosh, I have so many notes and I can't find what I'm looking for, feel free to just make yourself a little note card just so that you don't have to leaf through everything, so that you have the most basic information on that note card. It might save you a little bit of time. Okay, any questions on page 1 as far as the definition for hyperbola or any of the properties so far? Okay. And if you took Algebra 2 in high school, you've probably already talked about these, so hopefully it's going to be a little bit of a review for some of you. Okay. So the first thing we're going to do is just start out kind of basic here and find the vertices and locate the foci for the hyperbola. So let's start there. We'll first locate the value of a squared. Then we'll talk about what the value of a must be. And then from there, we'll look for c to determine the foci. So remember that for hyperbola, a squared is always in the denominator of the first term or the positive term. So we would say that a squared is 121. Now, let's see, if we're going to have to list these as ordered pairs, you'll probably want to think about the way that your hyperbola is oriented. Because of the fact that you have an x squared in the positive term, you know that you have a horizontal transverse axis. And if you need to look, if you're not sure, go back to this sheet and look at the form. So you had here a horizontal transverse axis, and you had x squared over a squared. So we're just kind of comparing that to what's happening here. So your hyperbola are going to open left and right. So you always have those definitions to look back on. So I'm going to say that we have a horizontal transverse axis. That means our hyperbola opens left and right. Sometimes I just kind of note that by just doing a very general, vague sketch of what the hyperbola is doing. Does it open left and right, or does it open up and down? Just so I'll know what's happening. And then my transverse axis has to run through there. So if we know a squared is 121, we know that a is 11. That must mean that our vertices are going to be 11 units to the left and to the right of the origin. Now, very similar to what we saw for circles and ellipses, we can tell that we're sitting here at the origin because we're not taking anything away from x or y. We're not adding anything inside those squares. So as long as you just have x squared and y squared, not x minus h squared and y minus k squared, then we know that this is centered at the origin. So you know that your vertices have to lie to the left and to the right of the origin. So our vertices are going to be listed at -11, 0, and 11, 0. And then we'll find the foci. And if I asked you to do this on a test and you just wrote plus or minus 11, comma, 0, that's fine. So we know that a squared is 121 and b squared is 81. So let's see, we have c squared in this case is a squared plus b squared. And remember, we kind of have to have that in this instance because sometimes a squared is going to be less than b squared. So we won't always be able to do that subtraction problem. So that's one way that you would know right off the bat, like, wait a second, maybe I used the wrong formula. So it has to be plus in this case for the foci. So let's take c squared is 121 plus 81. And you'll get 202. And that means that c is the square root of 202. I don't think there are any perfect square factors because you can't do 4. You can take a quick look to see if this can be simplified. I don't think that 202 has any perfect square factors. Let's see, 4, not 9, 16, 25, 36. No, you'll exhaust this list pretty quickly. 49, let's see, 64. No, I'm not finding any. So we should be good here. 81. Okay. So we can go ahead and write the foci as plus or minus, or we might as well use the same format here. Negative square root 202, 0, and positive square root 202, 0. Now, if you're trying to do a quick eyeball check to see, like, does my answer make sense? Remember that for hyperbola, our foci actually lie further out, because the foci, going back to page 1, have to always be inside the curves. So in this case, your number for C actually has to be bigger than the number for A, because you have to be able to go from the center beyond A to get inside the curve. For ellipses, that's why you had that minus sign to find your foci. But we have the plus here because we need to go out this direction so that our foci lie inside the curves. And same idea, the further away the focus is from the curve, the wider your curve is going to be. The closer your focus is to the curve, the more narrow it's going to be. All right, do we have questions for number 1, technically 1A? Okay. I see not a single one of you, so it's basically just like I'm recording a lecture by myself here at this point. Questions? Okay. Okay, so let's do the same here for 1B. Now, in this case, the y squared term comes first. That's the positive term. So we know that we have a vertical transverse axis. Oh, F is for the foci, V is for the vertices. No problem. I'm here to help. All right, so we have a vertical transverse axis. That means that we have a vertical axis and we have vertices that run through that axis to get to our vertex points here. So a squared is always going to be in the denominator of the positive term for hyperbola. So we have a squared is 25. So a equals 5. Now, because we have a vertical transverse axis, we're going to go from the center. We know we definitely have a center at 0, 0, but we're going to go from the center and we're going to go up 5 points and then down 5 units to get to our vertex points. So for our vertices, we're going to have 0 and plus or minus 5. Questions on the vertices? Okay. For the foci, we're going to find the value of C. So we know that C squared is A squared plus B squared, which is 25 plus 16, which is 41. So we know the foci also have to lie along this transverse axis. And we're going to go ahead and list those at 0 and plus or minus the square root of 41. And the square root of 41 must be more than 5 because 41 is greater than 25. So that's good. That's what you're looking for. Questions on 1A or 1B? Well, then it kind of has to be greater because if you're adding up A squared and B squared, it has to be greater than A. The only thing I was thinking was you might accidentally get this formula mixed up with the one that you use to find the foci for ellipses. So you might be like, okay, fine, C squared is A squared minus B squared. And then you run into an issue where you get a number that's smaller, and then you're going to double check it and say, oh, wait, that can't be. I must have done something wrong. And then you'd go back and figure out that wait a second, I used the wrong formula. So make sure that you're using the formula with the plus sign, and that, or make sure you didn't have any sort of weird computation errors. Does that answer your question? Okay. All right. Find the standard form of the equation of the hyperbola satisfying the given conditions. So this is where we're given information, and we're going to work our way backwards to find the equation for the hyperbola. So the main thing, the first thing we need to determine is, does the hyperbola open left and right or up and down? So we need to figure out what is the form of the equation before we do anything else. Anytime you're being asked to write an equation given information, I always suggest you jot down a quick sketch. It doesn't have to be beautiful, but just something so that you have an idea of what's going on, just so you can get a basic equation to use to move forward with. So if you have vertices at 0 and then plus or minus 7, then it must be the case that your hyperbola opened up and down, because they have to go through these vertex points. So something like that. Clearly, it's probably opening wider than what I have shown, but it doesn't have to be perfect sketch, just something. Put down something so you have an idea of what's happening. So since you know that, you know the form of your equation has to be y squared over a squared minus x squared over b squared equals 1. Now, if you're wondering, well, how do you know that? Well, you know that y squared has to be the first term, the first term's numerator, I should say, because of the fact that you have these hyperbola that are opening up and down. That means you have a vertical transverse axis, and you have to be of this form. We also know for certain that the center is at 0, 0. Now, you probably assumed that because we haven't talked about moving the center yet. That's true. I wouldn't do that to you if we hadn't talked about it yet. But you know that the center is equidistant from these two vertex points, and we haven't moved anywhere left or right. So the center is at 0, 0, so we don't have a y minus k, x minus h situation occurring. Now, A is, of course, guided by wherever your vertex points lie. So we know that A, in our case, has to be 7. Because that is how far your vertex point is from the center. Either one of them, doesn't matter which one you're looking at. So we're 7 units away, A units away, gives you a vertex point. So A squared is 49. So we can start to fill this out. And then the only thing we're missing is B squared. Well, you don't have B squared, and you can't really obtain that from the quick sketch that we put together. But we do have information about C, because we know that C guides that focus point. And you know that the focus points are going to be 9 units away from the center. And since you know the focus points are 9 units away from the center, you know that C equals 9. Now, if you know that C equals 9, you know that C squared is 81. And we also know that C squared is A squared plus B squared for a hyperbola. So we now can write down that we have 81 equals 49 plus B squared. Now, we don't actually have to solve for B here. We just need B squared so that we can pop it in for B squared in the formula. So 81 minus 49 gives you 32. And there's the equation for this hyperbola. Do you guys have questions on number 2? Okay. Number 3, match the equation to the graph. Okay, you do this one. Oh, wait. Take a minute and figure out which graph has to go with this particular equation. Is that good, Michael? Okay, no problem. So first you're going to determine which form the equation has to follow. I'm sorry, which opening your hyperbola needs to follow to match the equation. Then think about A and, well, just A, I guess, at this point. Okay, so this particular equation follows the form for a horizontal transverse axis. And if you have a horizontal transverse axis, your vertex points have to go through it. So you must be opening left and right. Okay, so we know that because we have x squared as the first term that follows this type of graph. We also know that your vertex points must be a units from the center. Your vertices are going to follow from a squared equals 4. So if a squared is 4, then a is 2. Now, don't be fooled because you had an option that was here to fool you, and that option was b. So if you chose b, you were just thinking about a squared and you were not actually thinking about a. So in order for your graph to match the given equation, you actually have to go with d. So d is the one where you have a graph that opens left and right, and the vertex points lie at 2 and -2. So it must be D. Does anyone have a question on number 3? Okay. Then let us discuss hyperbolas centered at the origin and how to graph them. So far we've talked about their equations, and we've talked about matching a graph. We've talked about finding vertices and finding foci. But now we'll talk about how to actually graph these hyperbola. It's slightly more complicated than graphing an ellipse, but it's not too crazy. Okay, so the hyperbola x squared over a squared minus y squared over b squared equals 1 has a horizontal transverse axis. We already talked about that. It also has 2 asymptotes. One of them is y equals b over a times x, and the other one is y equals negative b over a times x. And yes, technically you can highlight this because you will find this to be very useful. Personally, I just like to look at the rise over run on the graph. So let's look first at the graph that goes with the horizontal transverse axis. This one goes with the next equation. So let's focus here on this graph. So if you're confused about like, oh my gosh, asymptotes, as soon as you bring asymptotes in, you lost me, I'm so confused. Don't be. Look at the graph. Look what's happening here. In order to graph this hyperbola, we've already talked about how to find the vertex points. They are dictated by A. So we know that as long as we're centered at the origin, we just move over to A0 and negative A0, and we get these vertex points. But other than that, we don't know anything about how wide the parabola has to open. I mean, we know it's kind of controlled by the focus points, but what we also need to discuss is B's role in graphing this hyperbola. So what we're going to do when we graph hyperbolas is we're going to make this little box. We're going to first start out by making these 2 points, these 2 vertex points for our hyperbola that they're going to run through. The next thing we're going to do is we're going to mark points that are dictated by B in the other direction. So if we're talking about a horizontal transverse axis, you're labeling these 2 points for the 2 vertices. The next thing you're going to do is go to the y-axis and label these 2 points for, I sometimes call them your sub-vertices, but they're really just kind of controlling the asymptotes for your graph. Kind of tells you how narrow or how wide your hyperbola is going to open. So you're going to mark these 2 points for B, but you're not going to actually like graph any sort of vertex through them. What you're going to do then is you're going to make a little box. The box is going to be 2A wide and 2B tall. So what I tend to do is I put down the A points, I put down the B points on the other axis, and then I just create these corner points that lie along this width A and height B. So just if I were to move over to A, I would go up to B and create a point there. I would go down and do the same thing. Over here at negative A, I would go up to B and put a point, down to negative B and put a point. And then I just make this little dotted box. Now, technically, you don't even have to make a box. As long as you have these 4 corner points here, 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 and here, that's all you need. And what you're going to do then is you're going to use the corner points and connect the diagonals with a nice dotted line to create these asymptotes. So you're going to make the asymptotes first, then you're going to draw the hyperbola curve that goes through the vertices and approach the asymptotes. And again, these equations for your asymptotes, a lot of times you're going to be asked to give the equation, but when you actually graph these, you're really just using the box. You're not thinking about, okay, I need to graph the line y equals b over ax. But what you're really doing here, if you're thinking about this in terms of the slope, remember that y equals mx plus b. Well, the b in this case is 0 because we're sitting at the origin. So y equals b over ax means the slope is b over a. If the slope is b over a, that means the rise over the run is b over a. So don't necessarily think about, oh my gosh, I have to memorize this formula, and then I have to memorize that formula, and I have to know when is it a over b and when is it b over a. Just think about the slope in terms of rise over run. So your rise in this case will be b, your run is a. So you're going up b, out a. And we're going to do this a couple of times, so you're going to really see how it works. But a lot of times you're asked to graph the hyperbola and then give the equation for the asymptote. So like I said, you're not actually going to be graphing this line to get the asymptote. You're going to be using this box to get it. But you have to go through that perfunctory process of putting the equation down, basically. All right, so same idea here for if you have a vertical transverse axis. In that case, you have y equals a over bx and negative a over bx. Remember, of course, the negative one is the one that goes down from left to right. Down, so this would be the negative equation. That would be the positive equation as it moves up from left to right. So again, if you know that you have a vertical transverse axis, you're going to go up a units and down a units from the center. You're going to mark those. Put some points there. You know those are going to be your vertex points anyway. They're going to have to be there. Then on your other axis, you're going to go out B in both directions. You're going to make a box that has these corners that are dictated by A and B. So And again, you use this rise over run. So in this case that you have a vertical transverse axis, your rise will always be A and your run will always be B. That's why you have rise over run as A over B. That's why it is that way. All right, so you're going to make these 4 corner points, and then you're just going to run your asymptotes through them using a dotted line. And then once you do that, you can graph your hyperbola such that they go through the vertex points and approach the asymptotes. Okay, I just talked a lot. Does anybody have a question on what I just said? And it might be one of those things where you just have to see it in action. And then once you see it, it's like, oh, okay, that makes sense.
I kind of have a question.
Oh, tell me.
So basically you just square root like the standard form equation pretty much, and then that just gives you A and B, and then put B over A, and that's the slope.
Mm-hmm. If you're horizontal, if you have a horizontal transverse axis, it's B over A.
Yeah. Okay.
Yes. Yeah, but you're not square rooting the whole equation, but yeah, to get A and B, yes, taking the square roots of those denominators.
Okay.
Mm-hmm. Did you have another question about that?
No, that was it.
Okay, awesome. Anybody else? Okay. All right. Let's move on then to actually working on these graphs ourselves. And I have some instructions here for you that are actually from your book. To graph a hyperbola centered at the origin, locate the vertices. Use dashed lines to draw the rectangle centered at the origin with sides parallel to the axes, crossing one axis at plus or minus A and the other at plus or minus B. That's the box we just talked about up here. So depending on what type of transverse axis you're dealing with, you're either going to have A left and right or A up and down. So you're going to graph the box, use the dashed lines to draw diagonals of the rectangle, extend them out to obtain the asymptotes, and then draw the 2 branches of the hyperbola by starting at each vertex and approaching the asymptotes. This is going to be so fun. I'm not kidding. I really like this very much. Yeah, I'm going to do the first one, and then let's see. I probably have another one that you can do on your own. But if you would like to start working on this, be my guest. But yeah, I'll do this one, and then you guys will do the next one. Okay. All right. We have a vertical transverse axis. We know this because we have the first term having a numerator of y squared. So if we have a vertical transverse axis, we know that our hyperbola are going to open up and down. That's key. If they're going to open up and down, that means that A is going to be up A units from center and down A units from center. We also know that A squared is always going to be the denominator of this first positive term fraction. So we know that A squared is 9 and A is 3. Now, if A is 3 and I have a vertical transverse axis, I'm going to go up 3 units from center and down 3 units from center. Now, we have B squared is 25, which means that B is 5. So you are going to use the other axis to draw B. So you're going to go, instead of up and down from the origin, you're going to go left and right 5 units. Now, if you want to actually mark that as B, because I've actually had students draw the box and then they forget which way they're orienting their hyperbola, and they have the box perfectly and the asymptotes are perfect, but they accidentally graph it opening left and right instead of up and down or vice versa. So be careful. So you might want to label these just so that you know what you're doing. All right, now to draw your box, you're going to draw points at each of these corners. So there's going to be a corner at BA, which is 5, 3. So put your corner on there. You're going to have another one at B negative A, which is right here. There's another quarter of your box. Negative BA and negative B negative A. So really, in essence, you have 8 points here. If you end up getting really good at this and you don't end up putting B down, that's fine. You don't have to have it as long as you know how far out you're going. As long as you have these 4 corners, you're going to have these 2 vertex points. All right, before I proceed, does anyone have a question about how I obtained this box? I know that sometimes we have to type out our questions. And do you have this problem sometimes where you're chatting with customer support about something and they want to know what your problem is? And you're chatting it out and then they're like, oh, you're not responding, so we think you're gone, so we hang up on you. I don't want that to happen where you're like, I did have a question, but I'm typing it out. I'm trying to be patient and waiting because I know sometimes it takes longer to type things out. Questions? Wonderful. Okay, now get yourself a straight edge. Okay, fine, this will work. That's huge. Okay, get yourself a straight edge and connect the corners of your box. Now, of course, feel free to use the rise over run to just keep the slope going if you prefer to do that. But I think the easiest thing to do is just to use a straight edge and connect your corners. So that is one of your asymptotes. The other one is right here. And remember that these are going through your center point also. So you really have 3 points here that you're using to graph these. Do the best you can to make them look nice. You have 2 asymptotes now. Now, what I was saying about not memorizing the formula, because we also need to find the equations for the asymptotes. Don't memorize the formula, just look at what you have. You can easily just tell what the equation of the line is by using the slope, since we're centered at the origin. So you have a rise of 3 and a run of 5. So your rise over run is 3 over 5. So it must be the case that this asymptote is y equals 3/5 x. And this one that goes down from left to right is the negative version of that. Y equals negative 3/5 x. So when you're asked to find the equation of the asymptotes, you can just do that as long as they're labeled on your graph. You don't have to do anything else for that. If you, for some reason, really don't want to use the rise over run, you can always look back. And in this case, we're talking about the vertical transverse axis. So you're looking at a over bx and negative a over bx. A is 3, b is 5, a over bx, negative a over bx. So I'm just labeling mine and leaving them there. Now, that's all we have to do before we graph the actual curves of the hyperbola. So we found the vertices, we drew the rectangle, we used the dashed lines to draw the diagonals, and now what we're going to do is draw the hyperbola. You're going to start at each vertex. Hopefully you have it labeled nicely. This is where I'm just cautioning you. Don't have a perfect box and then accidentally draw your hyperbola left and right. Be careful. Make sure you remember what you're doing here. This one's going to go up and down. That's why at the beginning I like to just write it down so I don't forget. Use your vertex and the asymptote to kind of guide your hyperbola out in each direction. So start here at your vertex and then use the asymptote to just sort of guide your hyperbola up and to the right. Now it should look like it's approaching the asymptote but not touching. So do the best you can. As long as it looks like it's approaching, that's fine. I've had students who, I kid you not, will do something like this. Don't do that. I mean, it's really not that far of a stretch, I guess, that people would do this. This is not approaching the asymptote. This starts to approach and then it heads further away from the asymptote. That's not good. That's not what approaching the asymptote looks like. So start at the vertex and then just sort of approach that asymptote. It's beautiful. Oh, and I have blanks down here. So vertices, fine. They were at 0 and plus or minus 3. And we already said your asymptotes were at y equals plus or minus 3/5 x. And that one's done. Any questions about graphing a hyperbola centered at the origin? Okay. Now the next one, I will have you graph on your own. I want to get you started though, because this one is not written in standard form. Remember that a standard form equation, whether it's an ellipse or a hyperbola, is going to have a 1 on the right-hand side. In order to get 1 on the right-hand side, you're going to have to divide each term by 36. But 4 divided by 36, well, cancel out a 4 and you get 9 in the denominator. So you'll have x squared over 9 minus y squared over 4 equals 1. My kids are so loud tonight. I don't know if you guys hear that. Oh, they're so loud. Sounds like they all have boots on too, and they're just clod hopping around down there. Very odd. Beat them? No. They're so cute. You know, they're just kids. They're a little wild sometimes. A little wild. I yell at them a lot. Yell at the children. Doesn't do much. They get used to it, you know. They ignore it. All right, you guys work on your graph and we'll see how you do. Back in the old days when I was teaching, my husband used to take the kids to Hooters. And they reminisce about that. They can't go anymore. They were part of the Hooters Kids Club. And they ate fries. Yeah, I know. So weird. My husband keeps saying, what's the big deal? They're just wearing short shorts. Whatever. There's they get like a little placemat with little games on it and things to decode, and it says like Hooters Kids Club, and they get like a little sticker. They loved it. They still talk about it. My 3-year-old was just telling me yesterday, like, oh, I wish we could go to Hooters. It's terrible. Yeah. Yeah. So they have nothing fun to do, so I can't even yell at them for being super loud. I know it's terrible. I guess a lot of families are in Hooters, he says. I don't go there. Not my speed. Yeah. That's what I thought. He told me it's like a family restaurant now. The decline of civilization. Yeah. Yeah, it's very kid friendly, I guess. All right, I hope we at least determined that we have a horizontal transverse axis. Oh yeah, it was either Hooters or the library. He took them to the library a lot. Sometimes the Chick-fil-A play area. They have like nothing to do. Our library's closed. You can't go into Chick-fil-A. They have nothing now. Nothing. All right. A squared is 9. B squared is 2. Oh, B is 2. B squared is 4. Getting ahead of myself here. A is 3. B is 2. Okay, so these are the values you need for the box. Because it's a horizontal transverse axis, your value for A is left and right of the origin 3 units. So these are your vertices A. And then you're going to go up 2 units. And if you want, you don't even have to use the y-axis at all. You can just go up 2 units, down 2 units, down 2 units, and up 2 units, just to make that box. As long as, oh, this pencil, I cannot see. I turned on an extra light. I don't know if it looks different to you guys. It looked fine on the screen, but when there's too much light, I cannot, my pencil, it's like too shiny or something. There, that's where it should be. Okay, so that's your box. Go ahead and connect those. And you've got some asymptotes. And since you're going to have to list the equations for the asymptotes, take a look at the rise over run. The rise is 2, the run is 3. So you have y equals 2/3 x or y equals negative 2/3 x. But it's, remember, b over a if you have a horizontal transverse axis. And you might get used to that and you might remember that, and that's fine. Your vertices are at ±3 and 0. And then since you're opening left and right, you're going to use this point at 3, 0 to make your right side hyperbola. And then at -3, 0, oh, got a little bit close there, a little bit too close. Oh, well, I'll leave it there. So that's what you should have. You're opening to the left and the right. Does anybody have a question on this one, or the vertices or the asymptotes or any of these pieces of information? All right, well, now that you have gotten used to using this box to draw the hyperbola, you can now work backwards to find a standard form equation for the hyperbola. Go ahead and look at the box. The boxes for 6 and 7. If you want to work ahead, be my guest. But your vertices lie at A, and the top of the box or the bottom of the box will be dictated by B. So A would in this case be 5, because that's where you have a vertex for the hyperbola. Now you know that's A and not B because your hyperbola is actually running through that point. The hyperbola never runs through B. It always runs through A. So we have A equals 5, and then B will be dictated by how high the box goes in this case. B is 2. And we're centered at the origin. So since we're centered at the origin, we just need to pick the form for the equation for the hyperbola. Since we're opening left and right, we know that we have a horizontal transverse axis. So it must be the case that we have x squared over a squared minus y squared over b squared equals 1. And then just fill in a squared and b squared. Pretty straightforward, right? You guys do number 7. Unless you have questions on number 6, please feel free to ask. So your hyperbola is opening up and down. You have a vertical transverse axis. That must mean that A are these points on your vertical axis. So we would say that A equals 2. And then B lies on your other axis. So B would be 4. A squared is 4. B squared is 16. And this happens sometimes with hyperbola. Remember with ellipses, you always had that A squared was greater than B squared, or A is greater than B. Not always the case with hyperbola. And you'll see that because A and B dictate the slopes for the asymptotes, that's why you're going to get this changing of the shape depending on the size of A and B. Like if A and B were the same, then you would just have these straight diagonal asymptotes. But once they start to differ, depending on the slopes of those lines, you're either going to get hyperbolas that are super narrow or very wide. And in this case, B is greater than A, and you end up with this very wide hyperbola. All right, so we know we have to be of the form y squared over a squared minus x squared over b squared equals 1. And then you'll just fill in the rest. What I find kind of interesting about ellipses and hyperbolas, or you learn ellipses and then it seems like, oh, that was easy, and you get used to doing it. And then you learn hyperbolas, and at first it's kind of confusing because some things change, but you get used to working with hyperbolas and then it seems fine. But then something happens once you kind of mix them together and you're looking at two of them in the same section or something, or you're working on a test and you have an ellipse and then you have a hyperbola, and then it starts to get confusing because you're like, wait a second, which one has the fact that A has to be greater than B? Which one has the fact that like the A squared has to be in a specific term? And it starts to kind of get confusing. So kind of try to work your way back and forth between these so that you get used to knowing the properties for each one, that you will know. Okay, now we'll talk about graphing hyperbolas that are not centered at the origin. You knew it was coming. It's not that big of a difference here. The main thing is you're going to be looking at equations where you have x minus h squared instead of just x squared, and y minus k squared instead of just y squared. And that's the only real difference here. Anything else, if you have to label the vertices, not a big deal. You're going to graph them, so you're going to know where they're going. It's not like you're going to have to memorize a formula. You're going to be plotting them. Obviously, the equations for your asymptotes will change because you're not dealing with a center at the origin anymore. So we're going to talk about how this will affect your asymptotes. But other than that, everything is going to be the same. We're just going to be shifting it around, just depending on those values of h and k. So we're going to have this form of the equation if we have a horizontal transverse axis, and then we'll have this one if we have a vertical transverse axis. So everything else, foci still follow this equation, totally the same. Okay. Number 8. Use the center, vertices, and asymptotes to graph the hyperbola. Locate the foci, find the equations for the asymptotes. We're going to graph this one, and then on the next page, we're going to work on getting equations into standard form and then graphing what we come up with. So those are going to be a little bit longer. This one's going to be your more straightforward graphing question. So if you have questions, make sure you ask on number 8 before things get a little bit crazier in 9 and 10. Okay, first things first. Because of the fact that with hyperbola, you can have the y term first before the x term. Usually with ellipses, you saw the x term first. Be careful and make sure that you're noting which one is H and which one's K. Now, luckily in this situation, you have X as the first term, but these could be flipped. You could have a situation like this. And in that case, it's really important that you're careful not to say that your center is KH. Your center is always going to be HK. Don't think about this from left to right. You have to have H be the quantity that is subtracted from X, and K has to be the quantity that's subtracted from Y. When we get to a place where I think that'll be an issue, I'm going to make sure I point it out to you, just so that you understand what I'm trying to clarify here. Okay, H is going to be 1 because it's being subtracted from X. So we have H is 1, and K, well, we could really write this as Y minus -1. So K is going to be -1, or if you're thinking about it as being the opposite, then just take the opposite. This is your center. If you would like to put the center down, that's probably not a bad idea. So we're going to be at 1, -1. Just to plot it, you can make sure it's there. Okay, now it's also important that we discuss the values for a squared and b squared. Remember that a squared is always in the denominator of the first term. It does not have to be the larger number. A squared is 4, a is 2. It's also important that we discuss the opening of the hyperbola. This one has a horizontal transverse axis because the x squared term comes first. So we know it's going to open left and right. And since we know that, we can go ahead if you'd like to plot the vertices. That's probably not a bad idea. Since a is 2, we're not going to plot our vertices at 2, 0 and -2, 0. We're going to use our center, and we're going to go 2 to the right and 2 to the left from the center point. So from center, which is at 1, -1, I'm going to go 2 to the right and 2 to the left. Those are the vertex points. And if you want to label them as V or label them as A, whatever you like, I kind of want to label them as V in this case, just because I want to make sure it's super clear where our hyperbola are going to go. Now, a lot of times you're asked to write down the actual points for the vertices. So since you just graphed them, I would just jot down those ordered pairs. So we would say that the vertices are going to be at, let's see, 1, 2, 3, -1, and -1, -1. Now, I didn't actually ask you to label the vertices here, but you might be asked to do so on my math lab, and I might ask you to do so on an exam. So make sure you know how to find those. And remember that they're going to be equidistant from the center point. So 1 is between 3 and -1. Questions so far? All right, we have B as 3 because B squared is 9. If we know B is 3, we're going to start at the center and then go in the opposite direction 3 units. So 1, 2, 3. And if you don't want to draw those points, just automatically draw the corners. That's fine too. I'm just going to draw all of them because why not? And then we'll go down 3 units. So 1, 2, 3. And then I'll line those up with my vertex and draw the bottom of this rectangle. These little dots are so hard to see. All right, now that you have your rectangle, go ahead and connect these corners with some nice asymptotes. And don't go ahead and write the equations yet. I'm going to show you how to write the equations since our center is not at the origin. And we also are going to have to list the foci too. So we do have a little bit more work to do here. I'm going to line up my corners. And remember that your asymptotes should not be solid lines. They should be dotted lines or dashed lines. They don't actually exist on your graph. They're just guides, imaginary guides. If you'd like to write the slope of the lines, you can do that. So you know that from the center point, you went up 3, right 2. So your rise over run was 3/2. So the slope of your line is 3/2. And then the slope of this one is -3/2. And then we'll use that to write the equation in just a minute. If you really like the formula, go back and use the B over A. That's fine. That's essentially what we did anyway. Okay. So now we have the asymptotes down, and all we need to do at this point is use the vertices to graph the hyperbola. We are opening left to right. I'm glad I labeled these as vertices, otherwise I might accidentally draw in the wrong spot. So we're going to approach the asymptote, try to make these look curved and not like V's. Sometimes it's really hard to make these not look like V's. Do the best you can. I'm not going to be super picky, but I do want to have it at least look like you're approaching the asymptotes. Definitely not look like they're going away from the asymptotes. And they do need to be going through the vertices. Oh, and by the way, these are not functions. So you can't graph these using the y equals menu on your calculator. You'd end up with 2 different equations representing these. It'd be really crazy. Most of your calculators have like an app in there that'll graph conics, not all of them. If you don't have it, it's not a big deal. But if you're interested in looking for it and finding out, stick around for the office hour and I'll show you. I'm not going to demonstrate it in class because not everybody has it. Some of them work differently than others. Okay, so we're not done here. We have the graph. We need to locate the foci, and we need to write down the equations for the asymptotes. So we're going to go ahead and find c squared so that we can find c to discuss the points where the foci are located. So we know that c squared is a squared plus b squared for a hyperbola. A squared plus b squared is 4 plus 9, which is 13. And that means that c is plus or minus the square root of 13. Now, in order to get the actual ordered pairs for the focus points, we're going to start at our center, and we're going to note that our focus points have to lie inside the curves on this transverse axis. So while we're at the center point, we're only going to move to the right to get to this focus point and to the left to get to the other focus point. So I'm not going up or down anywhere. So the y coordinate of the center is not going to change. But to list out my foci, I'm going to take my center point. My x coordinate is 1. And I'm going to add the square root of 13 and take away the square root of 13. And then I'm not going anywhere up or down, so the y coordinate stays -1. And you can always write this as 2 different points if you'd like. I'm just going to leave it as 1 point. If you had some weird situation where the focus somehow ended up being an integer, like, I don't know, 2, then I would expect you to simplify this out. But since it's a radical, I don't want a decimal approximation. Leave it exact. And my math lab will also instruct you to leave your exact answer using radicals, blah, blah, blah. Before I talk about the asymptotes, are there any questions on the foci? Okay. All right, so let's talk about the asymptotes. Normally, if we're centered at 0, 0, we're going to have to correct for this. We would say that y equals b over a x, as long as we had a horizontal transverse axis. Or if you didn't even want to have to remember that, you could say, okay, well, I know that if we were centered at the origin, we would have this case. We need to correct for that by using our new center. So we're going to correct for the center 1, -1. I should say if, just so that that's clear that that's not the equation for the asymptote. So if we were centered at 0, 0, we would have y equals plus or minus 3/2 x. But we're not centered at 0, 0. We're centered at 1, -1. The way you're going to write this is instead of using y equals, you're going to go back to your original equation, y plus 1. So this is from standard form equation. From right here. So instead of using y, we'll use y plus 1. And then we'll keep the plus or minus b over a. So we'll have plus or minus 3/2. And then instead of using x, we're going to use x minus 1 just to correct for the center. And you don't have to simplify these. I used to make my students simplify them. This book doesn't require you to simplify them. And since you're not required to do so on your homework, you're not practicing it, I'm not going to require you to do so on the exam. So you can leave your asymptote equations just like this. So if your center is not at the origin, no big deal. Go back to your original equation. Instead of y, substitute whatever this value is. In this case, it's y plus 1. And instead of using x, go back to your original equation and then use whatever expression is in there for x. In our case, x minus 1. Don't forget the plus or minus. You can leave it like this. You don't need to distribute and subtract 1 and all that. Just leave it. This is fine. This is how your book leaves it. Questions on the asymptotes? Wonderful. All right, now we're going to put it all together. We are going to also talk about how to switch our equation from general form into standard form. So we're going to get a standard form equation. We're going to find A and we're going to find B. We're going to make the box, draw the asymptotes, connect the vertices with nice smooth curves. And then we're going to write down the foci and the equations for the asymptotes. Okay, I'm going to do this one, and then I'm going to have you guys work on the next one, at least parts of it, and we'll kind of catch up and see how we're doing. Now, I said last time that whenever you're working on completing the square, put the variables that go together. So these like variables, x squared minus 2x, those will go together. And then minus 25y squared minus 100y. And then move your constant to the right-hand side. Check and make sure you didn't accidentally switch any of your signs. Make sure everything stays the same. Now, things got a little bit more complicated when we did this for ellipses in 7.1, just because we had these coefficients to consider. And they're going to get slightly more complicated again, because when we're talking about hyperbola, we're going to have a minus sign that's involved. So we're going to have to factor out a negative. So I'm going to walk you through this. Now, as far as your first terms are concerned, you don't have very much going on here because you don't have a coefficient on x squared that's other than 1. So we're just going to go ahead and complete the square right here. Yeah, I guess we'll just do that now. Okay, so half of 2 is 1. 1 squared is 1. So we're going to add that to both sides. And then we're going to work on factoring a little bit here because we're not quite ready to complete the square here because you still have a coefficient on y squared that's not 1. And remember, we have to factor that out. So we're going to have minus 25. Don't take out a y. We're not going to factor out the GCF. We just want to take out that coefficient. So take out a negative 25. Keep that minus sign on there. It has to come out because you have a hyperbola. Now what you have left in your parentheses is y squared. And be careful. When you're factoring out a negative 25, this sign is going to flip. So you're taking negative 100 and dividing by negative 25. And what you're going to end up here with is positive 4y. Always go back and double check and make sure that your signs are correct. If you were to redistribute this, you'd have negative 25y squared and minus 100y, which is exactly what you're supposed to have. Now, once you have this, you can go ahead and complete the square inside the parentheses. Half of 4 is 2. 2 squared is 4. And then we'll discuss what needs to be added on both sides. Before I continue, does anybody have a question here? Because a lot just happened. If you're not sure about something, let me know.
Where'd you get that second plus 4 from?
This one, so when I completed the square, I took half of the middle term's coefficient. So I took half of 4, which was 2, and then I squared it and added it on.
Oh, okay.
Do you remember when we did this in 1.5 when we were using completing the square to solve quadratic equations?
Yeah, I do now.
Okay, yeah, so same idea. Take half the middle term's coefficient, square it, and add it on. And don't think about this outside coefficient because that'll sometimes throw you off. Just work inside the parentheses. Half of 4 is 2. 2 squared is 4. Thank you for asking. Does anyone else have a question? Okay. All right, so let's think about what we added in here. On the left-hand side, we added a 1 that wasn't originally there. So we're going to have to also add that to the right to keep this balanced. And then be very careful because in the second set here, we didn't really just add 4. We added in 4 times negative 25, which is negative 100. So this came from 4 times negative 25. This guy right here. So we need to account for that on both sides of the equation. Does anyone have a question there? Okay. All right, let's complete the square on the left, simplify on the right. On the left-hand side, keep your variable to the first power. Keep the sign behind it and take half of the middle term's coefficient, square the quantity. X minus 1 times x minus 1 is indeed x squared minus 2x plus 1. In the next term, you have minus 25, and then we're going to complete the square inside the parentheses. Keep the variable to the first power, keep the sign that comes behind it, and then take half of the middle term's coefficient and square the quantity. Y plus 2 times y plus 2 is indeed y squared plus 4y plus 4. On the right-hand side, you have 125 minus 100 is just 25. Questions here? You have several of these on your homework, by the way, from 7.1 and from 2.8, because I want you to get really good at this. Usually students get pretty good at this. You just have to practice. Practice makes perfect. All right, now I need a standard form equation. I don't have that. I have 25 on the right-hand side, and I need a 1 on the right-hand side. So we're going to go through and divide every term by 25. And what you end up with is x minus 1 quantity squared over 25 minus y plus 2 quantity squared over 1 equals 1. Now I know what you're thinking. Why did she bother writing a 1 here in the denominator? Isn't that technically unsimplified? Usually it is, and I don't have to write it, but it's really helpful when you're working with conic sections to keep your equations in this form. It's helpful to have this 1 here because that kind of more easily guides you to find that value of b squared. For some reason, if I don't write the 1 in the denominator, students are like, wait, b is 0. We don't have a hyperbola, and weird conclusions are made. B is not 0, it's 1. So normally, if there's a 1, we write it in the denominator. We have a horizontal transverse axis, which means our hyperbola opens left and right. Our value for a squared is 25. That means that a is 5. Don't go plotting at -5, 0, and 5, 0 because we are not centered at the origin. We are centered at, it's very important to write this down, 1, -2. It's a very important piece of information, so I want to box it off. And you know what? I tend to always say, as soon as you find your center, plot it. You don't want to forget about it. All right, a lot just happened. Does anybody have a question before I proceed? Okay. All right, I know we're opening left and right. I know that A is 5. I have the center plotted. So what I'm going to do right now is I'm going to plot the vertices. So I'm going to go to the right 5 from center. 1, 2, 3, 4, 5. There's one vertex. And I'm going to go to the left 5 from center. There's my other vertex. This is my center. Okay, so once you have your center and your vertices plotted, you're going to need to start making that box. And remember that in this case, the height of your box is dictated by b. If b squared is 1, that means that b is 1. So in order to make the box, I'm going to go up 1 and down 1 from each vertex point. And then we'll connect these points with asymptotes. And do the best you can to make your asymptotes the correct slope. Here's one of them. And there's the other one. So in this case, the difference between A and B is pretty stark. We're going to have a very narrow hyperbola. All right, you got your asymptotes. Go ahead and connect these vertices with the wings of your hyperbola. Approach the asymptotes. Try to not make them look like these. You can help it. Try to make them look as curved as you possibly can. Oh, I hit the asymptote. I have to model proper graphing here, so I'm going to try to fix it. Something like that. All right, and we're not done. We still have to locate the foci and find the equations for the asymptotes. Before I do that, does anyone have a question on the graph? Okay. The foci, we need to find C for. We're going to use a squared plus b squared, which is 25 plus 1, 26. That means that C is plus or minus the square root of 26. And our foci are going to lie along that horizontal transverse axis. So I'm going to take that x coordinate for the center point, and I'm going to add and subtract the square root of 26 from it. I'm not moving anywhere up or down from the center. I'm just moving out to get to one focus point, to the right, and then to the left to get to the other one. Don't need the y coordinate for that. So for my foci, I'm going to start at my center point. The x coordinate is 1. I'm going to add on and take off the square root of 26. The y coordinate will remain unchanged. This is an important piece of information. We'll put a box around it. Any questions on the foci? Okay. The last thing we're going to do for this one is find the equations for the asymptotes. Notice the slope, if you don't want to look back, is rise 1, run 5. So we know that the slope is 1/5 and negative 1/5. So we'll use that fact to write the equations for these lines. Remember, we're starting with y equals. So instead of y, we're going to go back to our standard form equation, and we're going to use y plus 2. So we're going to have y plus 2 equals, and then take your slope, plus or minus 1/5. Use your parentheses, and then you have x minus 1. Bring that straight out of your standard form equation and into the expression for your asymptotes on the right-hand side. And you can leave it just like that. I know, it's just a thing. It's a hoop you have to jump through. You have to write the equations. Questions on number 9? So thinking ahead to your test for next week, Wednesday, this would be like similar to a question that you would have to do on here. However, on your test Wednesday, I might give you something like, take this general form equation and turn it into a standard form equation. Tell me what kind of conic it is, and then find the required information. And then I'll have a list of information you need to find depending on what kind of conic it is. So I might not tell you. You might just have to look at the equation and think about it, like what happens. Like, oh, well, this obviously has a plus and that one has a minus. They have opposite signs, therefore this must be a hyperbola. If they have the same signs, it could be an ellipse, could be a circle. We'll talk about parabolas next time, and you'll see the difference there. So we'll really get more into the nitty-gritty of that next time when you know all of the conics, and then we can kind of compare them and talk about the different ways that you're going to see the equations presented to you. Okay. Now, we have one more. You start working on this equation, getting it in standard form. I'm going to give you a couple minutes. And then I'll check in on you. We'll catch up on the equation, and then you can work on your graph. I just realized I already gave you this equation such that the variables were right next to each other. Terrible. Okay, so the first thing you're doing is factoring out a coefficient, not a variable. So take out the 4, that leaves you with x squared minus 6x. So negative 24 divided by 4 is negative 6. And then you're going to complete the square inside these parentheses. So half of 6 is 3. 3 squared is 9. So add 9 inside the parentheses, and then think about in a minute what you're going to need to add to the other side. It's a little bit trickier for the y's because you have a minus sign here. So take out a negative 9, then write your parenthesis. Then you have a y squared. Negative 90 divided by negative 9 is positive 10. And you have a y on that. You can always go back and check. Negative 9y squared, negative 90y. Complete the square inside the parentheses. Half of 10 is 5. 5 squared is 25. And I meant to move left, and I totally did not. I tried to do it for the other row, not this one. Okay, now, what you really added on the left-hand side was 4 times 9, which is 36, and negative 9 times positive 25, which is negative 225. So on the right-hand side, you have 153 plus 36 minus 225. Now, if you're wondering, like, this quantity is negative, what's happening? That's good. This is going to be very instructive. Let's go ahead and complete the square on the left, simplify on the right. X minus 3 quantity squared, and then minus 9 times y plus 5 quantity squared equals 153 plus 36 minus 225, negative 36. Now, this doesn't mean that all is lost, because remember that in order to get a standard form equation, you still have to divide both sides by this coefficient. Just because it's negative, that's okay. Divide all of these terms by negative 36. And you will see what happens. This happens sometimes. It's not a big deal. So you're going to get negative x minus 3 squared over 9 plus y plus 5 squared over 4 equals 1. And whether you put the negative in the denominator or in front doesn't matter. For this term, you have a negative divided by a negative, which gives you a positive. When this happens for a hyperbola, it's not a mistake. Just switch the order of the terms so that you see subtraction here. So write the y squared term first, and then you'll write the x squared term. That is the standard form equation for this general form hyperbola. Does anyone have a question on the equation? Because that's a lot of the battle here. If you can't write the equation, then how are you going to graph the hyperbola? Okay, we only have 3 minutes left, so I'm going to wrap this up for you. And if you have questions, I hope you'll stick around for the office hour. Okay, very important to note that your center here, HK, is going to be flipped in this. You cannot read it from left to right. H always corresponds to X, K always corresponds to Y. So your center is actually at 3, negative 5. I've seen a lot of students think about that as left to right instead of X being with H and Y being with K. So be very careful with that. X minus H, Y minus K. So your center's at 3, negative 5. Go ahead and plot it. Then you have A equals 2, B equals 3. If A equals 2, and we need to note here that our transverse axis is vertical, that means that your hyperbola is going to be opening up and down. That means we're going to go from center up 2 units and down 2 units to get to the vertex points. So there's one. Here's another one. Now that you have your vertex points, use B to draw that box. So you're going to go the other direction, 3 units to create your rectangle. 3 units, both directions. And then you're going to connect these with some nice straight dotted lines for your asymptotes. Here's one. And there's the other one. Oh. Lost a part of my asymptote there. Okay. We're opening up and down. So go ahead and make your hyperbola. Once these start to get off center, they start to look a little funky, but that's okay. And then the other 2 things we need are the foci and the equations for the asymptotes. So c squared is a squared plus b squared. That's 4 plus 9 equals 13. And that means that c is plus or minus the square root of 13. Now, in this case, your foci lying along that vertical transverse axis are going to go up and down from center. So in this case, the x-coordinate of your center is not going to change for the foci. They're still going to be located at x equals 3, but we're moving up and down from center. So start with that y-coordinate at -5 and go up and down the square root of 13 to get to your foci. And then last but not least, the equations for your asymptotes. If you want to look at the formula, that's fine. If you want to look at your rise over run, you rose 2, ran 3. So your slope is 2/3. We're going to take y plus 5 equals plus or minus 2/3 times x minus 3. All of that came from right here. Moved it right down here into this equation, and we're done. If you have questions, stick around. I'm going to put up some homework, but I'll be on for another 15 minutes for your office hour. Monday, we'll talk about parabolas, and I'm probably going to call them hyperbolas the whole time. All right, so 7-3, and then maybe we'll do a little bit of a review since your exam is on Wednesday. We're going to skip the quiz Monday. We don't have time for it. I'll probably send an email to remind you, but in case I don't, we're skipping the quiz Monday. Have a wonderful weekend, you guys. If you have questions, email me.